My name is Whitney Colella. I'm the president of Gaia Energy Research. This presentation is on state-of-the-art electrochemical hydrogen compressors in conjunction with Giner, a Boston-based company. Gaia Energy Research identifies design and control strategies for new energy systems and niche markets where they fit best. Gaia also looks at addressing commercialization bottlenecks and estimating future costs of new energy systems, for example, through design for manufacture and assembly models. Gaia also looks at life cycle assessment, the changes in emissions or in environmental impacts from changes in different energy technologies, and also independently reviews the technical performance and market prospects of new energy devices. Most of my background is in electrochemical systems and renewable energy, and a lot of what I do is building teams of academics, researchers, and industry participants for new proposals and projects. You may be familiar with my name from the book Fuel Cell Fundamentals, which is a textbook on fuel cells, and it's meant for juniors and seniors in engineering school and also first-year graduate students. So why are we interested in compressing hydrogen? One application is for vehicles, and another application is for grid storage. Gasoline, as you guys know, has about 3,000 times the volumetric energy density of hydrogen at atmospheric pressure. And most fuel cell vehicles need to store their hydrogen at 350 to 700 bar in compressed hydrogen tanks. So that's where we are with gasoline right now. This is where we are with liquid hydrogen and gaseous hydrogen compressed. The volumetric energy density is shown on the y-axis, and the gravimetric energy density is shown on the x-axis. Hydrogen can also be combined with reversible electrolyzers to store grid electricity and mitigate renewable intermittency, for example, with arbitrage balancing or power quality on the electric grid. And generally, the thought is to compress to 100 bar for those pressures. How do you compress hydrogen? Well, most mechanical compressors use a piston or a diaphragm. This is an example of a reciprocating piston compressor that moves the piston back and forth to squish volume of gas into a smaller volume. There's also diaphragm compressors, which are a similar concept. You're moving a flexible membrane forward and back to squish a volume of gas into a smaller volume. By contrast, electrochemical hydrogen compressors have characteristics of electrolyzers and fuel cells. Like an electrolyzer, an EHC consumes electricity, and in an EHC, the electricity provides the input energy needed to enable hydrogen molecules at one electrode, the anode, on a low pressure site to break into hydrogen's ions that are conducted through the hydrogen ion conducting electrolyte. At the high pressure electrode, the cathode, the hydrogen ions then recombine with the electrons to form hydrogen. Electricity provides the energy needed to move the hydrogen from low pressure to high pressure, from one side of the membrane to the other. And then EHCs also work in similar ways and in different ways to fuel cells. Proton conductivity across the electrolyte can be a function of the electrolyte's water content, as with a PEM fuel cell. And then unlike a PEM fuel cell, oxygen is not a reactant at the cathode, and water is not a product at the cathode either. So unlike a PEM, these factors do not influence performance. The oxygen activation polarization at the cathode and the concentration polarization due to water blocking reaction sites at the cathode. EHCs are dominated by ohmic polarization. I'm going to first summarize the results of this study and then go into it in greater detail, but I'm starting off with a summary of the main results to make sure at least that information gets across. So one main point is that in theory, electrochemical systems, electrochemical hydrogen compressors have the largest marginal energy efficiency gain over mechanical compression at the highest outlet pressures. However, in practice, based on manufacturer model data, this gain may be less. However, the manufacturers commonly overstate efficiencies on specification sheets compared with real-world operations. So the gain still may be substantial in practice. So that's talking about efficiency. When we look at cost, in practice, the EHCs have the largest marginal cost advantage over mechanical compression at the lowest outlet pressures. Equipment capital costs for mechanical compression more than doubled in moving from 100 bar to 875 bar inlet, compared with going from 1 bar inlet to 875 bar outlet. So it's 100 bar inlet to 875 bar outlet versus 1 bar inlet to 875 bar outlet, due to the large mass of equipment needed to handle large volumes of gas. Model results indicate that the greatest marginal cost savings or cost advantage for the EHC is between 1 and 100 bar. So the question we're trying to ask here is, what's the optimal outlet pressure for an EHC? Is it high pressure, like 950 bar, or is it low pressure, like lower pressures, like 100 bar? Based on efficiency, the higher outlet pressures may be where the greatest advantage is, and based on capital costs alone, the greatest benefit may be at the lower outlet pressures, like 100 bar. So this is a summary of the case study, case 1, where we're looking at 100 to 875 bar. For the EHC, the model results indicate that the primary cost driver is the electricity cost, or the electrical efficiency. The secondary cost driver is the capital cost. The tertiary cost driver is the warranty cost. For mechanical compressors, the primary cost driver is, again, the electricity cost or electrical efficiency, but the secondary cost driver is the fixed operations and maintenance costs. Mechanical compressors are infamous for having maintenance issues, and that shows up in the cost equations as well. The tertiary cost driver for the mechanical compressor is capital cost. All of that said, manufacturing costs can vary by manufacturer, and the compressors with higher capital costs may in some cases have lower maintenance costs and vice versa. The second case we're going to look at is going from a different inlet pressure, 1 bar, up to 875 bar, the same outlet pressure. So we've just lowered the inlet pressure. For the EHC, the cost drivers are modeled to be the same. In the mechanical compressor system, the model results indicate that the primary cost driver is, again, electricity cost, electrical efficiency, but the secondary cost driver is capital costs, and the third tertiary cost driver is fixed operations and maintenance. The marginal cost increase in going between 100 bar and 875 bar, and compared with 1 bar and 875 bar outlet, is about 30 cents per kilogram of hydrogen. That's where the largest potential economic gain is. These are summaries of the results that I'm going to go through in more detail now. Ideally, mechanical compression is isentropic, and ideally, electrochemical hydrogen compression is isothermal. Isentropic means constant entropy. Isothermal means constant temperature. The isentropic equation is shown on the left. The isothermal compression equation is shown on the right. As you can see, the isentropic equation is limited by the ratio of the specific heats, whereas isothermal compression, shown on the right, does not have this limitation. These are the same equations I just showed you, but they're plotted here. Theoretically, the EHC, shown in green, isothermal compression, can use less energy than mechanical compression, shown in red, or isentropic compression. The isothermal work is about 30% lower than the isentropic work at 10 bar. And then if you move up to 950 bar, the isothermal work is about 68% lower than the isentropic work. So this is a theoretical comparison, and it seems to indicate that the EHC can see the highest gains in efficiency at the highest outlet pressures. Multi-stage mechanical compression is modeled to require more than isothermal but less than isentropic compression. The figure shows the low end of the compression ratio, and the gray dot shows a data point from a compressor manufacturer called Ariel Inc. It's a 4-stage hydrogen compressor that it consumes a minimum of 1.88 kilowatt hours per kilogram, going from 1 bar to 34 bar outlet pressure. This work is the actual work is likely to be much higher than this. This estimate of the work required is based only on the electric motor load, but does not include pumps, control system, sensors, heaters, chillers, and other ancillary loads. It's based on manufacturer's model data, not measured data. This is another example of real-world data. This is multi-stage mechanical compression. It's modeled to require more than isothermal compression. This is another gray dot shown on the right, and less than isentropic compression. And basically, this is for an Ariel 6-stage hydrogen compressor that it consumes a minimum of 3 kilowatt hours per kilogram from 1 bar up to 375 bar outlet pressure. Again, this is based on manufacturer provided data, not independently measured data, and does not include all ancillary loads. Looking at this in detail, this is case number 1, going from 100 to 875 bar. These are some of the cost equations or cost data that go into the model for a mechanical compressor subsystem. Mechanical compressor subsystem cost data goes from 100 bar to 875 bar outlet at 10.35 kilograms per hour. The mechanical compressor subsystem is composed of Hydropack hydrogen compressors, and then 3 of them are needed in parallel to meet a specific DOE requirement of 31 kilograms of hydrogen per hour at that flow rate. The energy consumption was estimated as 4.3 kilowatt hours per kilogram for going from 100 to 875 bar. And then that's not inclusive of all the ancillary load work that's needed. The electricity price is about 6 cents per kilowatt hour based on energy information data. And then it's benchmarked against our electrochemical hydrogen compressor system, which has definitely achieved energy consumption as low as 5.3 kilowatt hours per kilogram of hydrogen and is going lower. So for the inlet pressure of 100 bar, the EHC, the isothermal compression can use less energy than a mechanical compression, as shown in this figure. The isothermal work is much lower than the isentropic work at the highest outlet pressures, and then the hydropack compressor's energy use is estimated at 4.35 kilowatt hours per kilogram. That's the gray dot in the top right. These are some of the input data that go into the cost comparison model. The left column shows mechanical compression, the right column shows the electrochemical hydrogen compressor. And the main cost difference is 66 cents per kilogram of hydrogen for the mechanical compressor system versus about the same cost for the electrochemical system. The main cost drivers, as we talked about before, for mechanical compressors are electricity costs, fixed operations and maintenance, and capital costs. And then for the EHC, the main cost drivers are electricity costs, capital costs, and warranty costs. Looking at the second case of going from 1 to 875 bar, for the mechanical compressor subsystem, we're assuming one aerial compressor going from 1 bar to 35 bar, and then 3 hydropack compressors as well. On top of that, the aerial compressor is about $1 million due to the large mass of equipment needed for low pressure and large volumes of gases. And the energy consumption for that compressor is 1.88 kilowatt hours per kilogram, and for the hydropack compressors, it's 4.35. The total energy consumption is about 6.2 kilowatt hours per kilogram, going from 1 bar to 875 bar. These results show for the second case, the mechanical compressor system is much more expensive, about 95 cents per kilogram of hydrogen compared with 66 for the electrochemical hydrogen compressor. Again, the mechanical compressor system's main cost drivers are the same, but they switch order. The main point I'd like to get across here is that there's a huge difference between going from 100 bar up to 875 bar versus 1 bar up to 875 bar. There's about 30 cents per kilogram of hydrogen. That's the largest potential economic gain where electrochemical hydrogen compressors can make the most benefit. To summarize, the EHCs have the largest marginal energy efficiency gain over mechanical compression at the highest outlet pressures. The measured efficiency data from the mechanical compressor installations at refueling stations could help elucidate this, and there's not that much measured data. This is based on manufactured data. And then the R&D progress is expected with the EHCs. We're already moving from 5.3 kilowatt hours per kilogram closer to 2.7 kilowatt hours per kilogram. EHCs appear to have the largest marginal cost advantage over mechanical compression at the lowest outlet pressures. And then the equipment capital cost for mechanical compression more than double and moving from 100 bar to 875 bar. Versus 1 bar up to 875 bar. The model results indicate that the greatest potential marginal cost advantage for the EHC is between that 1 and 100 bar savings area, 30 cents per kilogram of hydrogen. I'm also working on a project to develop an emissions database for the Middle East. If we're going to make an improvement, we need a baseline from which to measure that improvement. I'm working with my colleague, Professor Abdel Mohsen from the University of Cairo, American University of Cairo, to develop a database for Egypt's buildings for what their emissions are from those buildings. This is the first time such a database will be developed. It's partly sponsored by the U.S. National Academy of Sciences and Engineering and Medicine in the U.S., but we're also looking for additional funding. So if you don't mind donating $1 to this, we'd really appreciate it. I'd like to acknowledge the Department of Energy, also GINER, and my colleagues at RPI and NREL, and this is based on work supported by the U.S. Department of Energy.